Have you ever wondered why a magnet snaps to your refrigerator, but ignores a sheet of aluminum or copper? All of these materials contain electrons. So why do only a select few materials have the power of magnetism? The answer comes down to two things happening at the subatomic level: electron spin and domain alignment. Every electron behaves like a tiny magnet because of an intrinsic quantum property known as spin. But if every electron is a tiny magnet, shouldn't everything be magnetic? Not quite. In most atoms, electrons come in pairs. So if one electron is in a spin-up state, the other is in a spin-down state. Their magnetic fields point in opposite directions and cancel each other. So even though every electron is magnetic, the atom as a whole does not become magnetic. But what happens when an atom has an unpaired electron? The unpaired electrons give individual atoms a small magnetic field, and these atoms start acting like tiny magnets. But in many materials, magnetic fields of all these atoms point in random directions. This reduces the overall magnetic force generated by the atoms, and the material becomes weakly magnetized in the presence of an external magnetic field. These materials are known as paramagnetic materials. Aluminium is an excellent example of a paramagnetic material. In contrast to a paramagnetic material, a ferromagnetic material can be strongly magnetized by an external magnetic field. Iron is the most familiar example. In fact, the word ferromagnetic comes from ferrum, the Latin word for iron. In ferromagnetic materials, a quantum mechanical effect, called the exchange interaction, makes neighboring atoms prefer to have their electron spins pointing in the same direction. Quantum mechanics says that, for these particular atoms, the electrons have a lower energy, or in other words, more stable arrangement, when many neighboring spins are parallel. And nature always prefers lower energy arrangements. So millions upon millions of atoms align their spins. Now, if every atom in a large piece of iron pointed the same way, it would create an enormous magnetic field. But instead, the atoms in the ferromagnetic materials form regions called magnetic domains. Within each domain, millions of atoms align their electron spins in the same direction. But different domains point in different directions, so their magnetic fields largely cancel each other out. So an ordinary nail isn't strongly magnetic in the absence of an external magnetic field. But when you place a ferromagnetic material, let's say iron, inside a sufficiently strong magnetic field, magic happens. The external field forces those chaotic domains to team up. Domains pointing in the field's direction grow bigger, while others snap into alignment. Suddenly, trillions of micromagnets are all pulling in the same direction, turning the plain piece of iron into a powerful magnet itself. So, the next time a magnet snaps onto your refrigerator, remember, it's not just a piece of metal. It's billions of electron spins, organized into magnetic domains, all working together to create one of nature's most fascinating forces.